should work. Good. It should work. Don't you have an exam today, or a test, or is that just the chemistry people? Sorry? There is a test. And you are here, despite a test. That is dedication. I feel very honored. Good morning. Good morning. Most wonderful good morning. Good morning. Good morning. Most wonderful good morning. Most wonderful good morning. Good morning. Most wonderful good morning. Good morning. Good morning. Most wonderful good morning. Good morning. A very good morning. Good morning. Good morning. Most wonderful good morning. Good morning. Good morning. Good morning. Most wonderful good morning. Good morning. morning. Good morning. Good morning. Very good morning to all of you. Good morning. 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 Most wonderful good morning. Very good morning. 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 Most wonderful good morning. Good morning. Good morning. Good morning. Good morning. Carry on. Good morning. Good morning. Good morning. Good morning. Good morning. Good morning. Most wonderful good morning. Good morning. A very good morning to all of you. Good morning. Most wonderful good morning. Good morning. Good morning. Most wonderful good morning, good morning, good morning. Good morning. Good morning. I think there's a little bit of collateral by the sounds of it. I think Keynes College is a few glasses short now. Most wonderful good morning.
Hello.
Most wonderful good morning. Good morning. Good morning.
Sometimes.
Oh, absolutely. 4 minutes early. Good morning. Good morning. Good morning. Most wonderful good morning. Good morning. Good morning. Good morning. Very good morning to you. Good morning. Good morning. Good morning. Most wonderful good morning. Good morning. Good morning. Right, let's get started. Most wonderful good morning, everybody. I just said to some of your colleagues a little bit earlier, I feel quite honored to see so many of you here today, because I know that some of you have a biological chemistry test today. So what time is that test? 4 to 6. Oh, it's one of these online things. Oh, I see. Okay. Well, good luck. You will need it. Yeah, just try to boost a little bit your confidence. Right. What I want to do with you today is start a new topic, i.e. reaction kinetics. Why on earth are we going to do that? Well, A, it's fun. And B, we are going to need a little bit of insight into that, because next term, most of you, I don't think the bioengineers do that, but the rest of you are going to do a module on enzymes and metabolism, where we look at reactions that happen in a cell. And for that, we will need a little bit of understanding how these reactions proceed. So for example, what we are going to discuss in this module then would be, let's say we have a reactant A that is converted into a reactant B that is converted into a reactant C, and you get the gist. And that is really sort of a very simplistic visualization of a biochemical pathway, a toy pathway, if you like. And we need to figure out, for example, how best we can regulate this pathway. So, for example, if A, how do we get through glycolysis, breakdown of glucose to get energy? And there are some really interesting tools out there that we can use in order to analyze pathways. But in order to do that, we need to have a bit of an understanding of how we can formalize pathways like that, how we can formalize reactions like that. And that is what these few lessons on reaction kinetics will be all about. And also, I need some exam questions so that I, can ask you a few things. So might come up in an exam, might not. Don't know. Haven't set the exam questions yet. So if you piss me off, right, then got it? Anyway, let's start with a very simple question. What's the difference between speed? Yeah, and I don't mean the illegal stuff. What's the difference between speed, velocity, and rate?
Speed is just like how fast the thing is going.
How fast the thing is going, okay, yeah.
Velocity has a direction.
Oh, velocity has a direction.
I think rate is per something. So it will be like velocity.
Rate is per something. Oh, I love that. I love your definition. I absolutely, and I'll tell you in a minute why, right? So, speed usually describes something, a change per time unit. So a change in location. And as you rightly say, speed doesn't have a direction. So when you drive, for example, the speed tells you you are driving 65 miles an hour, which is too fast anyway, but it tells you that you have a distance, 65 miles, and you travel that in a time unit per hour. Velocity, as you rightly say, has a direction. So a velocity can be, in a way, can have a sign. Speed is always positive. And no, I don't endorse illegal substances, right? So speed is always positive. There's no direction. Velocity can be positive if you are going towards something, or it can be negative if you are moving away from something, right? Now, what is rate? What is rate? You've heard that before. What is a rate? You made a really nice attempt in defining it. Question. 65 miles per hour. Is that a rate? Could that be a rate? You don't have to put your hands up, just shout out. Yes, yes or yes? No? Okay. 65 miles per hour is not a rate. Okay. 10 millimole per second. Is that a rate? Yeah? Okay. 15 pregnancies in a year. Is that a rate?
Yeah.
Yeah? 5 donuts eaten per person. Is that a rate? Alex goes no. You go yes. We have a little bit of a sort of a discrepancy here. One says no, the other one says yes. Who is right? Well, here comes your definition into place. Rate is actually a really curious thing. A rate is defined as a change in something divided by a change in something else. That's the definition of a rate. So, if I say 15 pregnancies per year, so we have got 15 pregnancies that are a change in pregnancies per year per time unit. That's a rate. If I have 5 donuts eaten per person, this is something divided by something else. Again, that is a rate. Sorry, Alex. So if you can write it as something divided by something else, this is a rate. Or in other words, people might not see that as a rate, but it is a ratio. And ratio, because some people, especially when they are drunk, can't pronounce it, they just simply call it rate. So a rate is nothing but a ratio. For our purposes, we are not terribly interested in how many pregnancies or how many donuts eaten or something like that. When we are looking at something like that, we are more interested in changes in, let's say, concentration per time unit. Yeah? And we can, for example, say, if we are looking at something like that, we want to write what is generally known as a rate equation or general rate law. So, general rate law or general rate equation, where we say, right, the rate that we are looking at, and this rate, like velocity, has a direction. A rate can be positive or negative. If we see that something is increasing, then per definition we basically say it is something positive. An increase is positive. Why is that? Well, we can write, for example, in a very general form, as I said, we can write this as a change in something. Well, let's write it as a concentration. Change in concentration per change in time. So that is an example of a rate. It's not the definition of a rate, but that is an example for a rate. Now these funny delta things, you have come across them. Delta stands for? Why is it a delta then, if it's changing? You're right in a way, but why is it a delta? What could delta stand for? What?
Difference.
Difference, exactly. Delta stands for difference. Yeah? Greek, D, for difference. And you've started with thermodynamics, haven't you? Great. You like it, don't you? No? Oh dear. Well, one of the things that a lot of people struggle is, you see this delta G, delta H, delta U, and all that stuff, and you think, what's the definition? Now, this delta actually, delta means difference between the state after or I should probably say, no, let's write it like that. State after minus state before. That is what the delta actually symbolizes. A difference after minus before. So, for example, it won't happen to me for obvious reasons. That's me. I go to the hairdresser. Not that I need that. And I end up like that. If I want to determine the delta hair length, so delta hair length equals hair length this one minus hair length of that one after minus before. In this case, can you predict the sign for the hair length? Is it positive or negative, the delta? It's negative, exactly, because after it's shorter. Yeah, that makes sense. That is the definition of a delta. I want you to remember that. So if you've got delta G, for example, or delta H, you know that your H, and so you have, let's say you have delta G equals negative, you know that your energy after something has happened is smaller than the energy before it has happened. That is what this delta means, right? And when we talk about kinetics, we can write this as rate equals delta concentration over delta time. That would be, bless you, that would be a perfectly valid rate expression, yeah, with this delta. Now, delta actually has sort of another connotation in it. It means it is a very big change. So delta means macroscopic. So for example, 65 miles per hour. In a way, it's almost sort of when you drive, you know, you can easily figure out how fast do I drive. Well, from here to London, it's about 65 miles, and it takes me an hour. That would be expressed with this delta. But do you always actually drive exactly at 65 miles per hour? No, you don't. Right? There might be this bloody truck in front of you, and you have a pit stop at a service station, have a coffee. You then drive faster. You realize you forgot the wife at the service station, you return back, right? Pick up the wife, get an earful, yeah? And then you rush 120 miles an hour down, yeah, because you want to really get to London quickly now, and don't want to constantly. So what you can do is actually, you can say, right, I break that down in smaller and smaller units. And instead of this macroscopic observation with a delta, I make these units smaller and smaller and smaller. And instead of writing small delta and things like that, what you can do is you can write rate equals, and if you make these time units and changes in concentration infinitely small, you can write it as D concentration over D time. And this D that I write here, that is basically infinite small difference. So instead of saying per hour, you say what is my rate, what is my time, what is my velocity, what is my speed per 10 minutes, per minute, per second, per nanosecond, per, diddly squat second. That is what this D is. So that's the rate. Now let's think about it. If we write it like that, change in concentration over time, what would be the unit for rate? What do you think? What's the unit for concentration? Molar, exactly. So we could write mole per liter or molar, absolutely. So the unit, molar, and unit for time? Second, yeah, let's go for second. So we would have concentration per time and the appropriate units for our rate, like miles per hour or something like that. In concentration terms, it's concentration per time. That's the unit for a rate. Fantastic. Now, let's say we have a reaction where we have a reactant A, and this reactant A is consumed. And I just simply write it like that. A arrow, it means the reactant is consumed. I'm not telling you into it, what it is converted. Let's just go for that. I can now write just a very simple rate equation. I can say, right, my rate, and I write it as D, and I'm looking at the concentration of A, yeah? Because that is what I'm interested in. D concentration of A over time, dt, that's my rate, equals. Now, we have a consumption of our A. So do we have more A after the reaction has happened, or do we have less A after the reaction? Less A. So we take A away. So our concentration of A is less after the reaction compared to at the beginning of the reaction. And if that is the case, if we have a consumption, we indicate that in the rate law by a negative sign. Negative. Whenever you see a negative, you know there is something consumed. In this case, A is consumed. Yeah? And in a very general terms, we can write this further that the rate of this reaction depends on a constant, and this is abbreviated with the letter K, with a lowercase k. Why is it a K? Well, it's not because I can't spell properly. I know that constant is spelled with a C in English, but if you write C, then people might confuse it with the speed of light. So we have to come up with a different symbol. And because much of this kinetic stuff was developed at the beginning of the 1900s by German physicists. And in German, you spell constant with a K, so therefore you've got a K. So minus K times the concentration of A, and I write concentration with these square brackets. That's, common standard form. To the power of something. And we are talking about this symbol. Very often it's M. Some people abbreviate it N, P. Please don't use the symbol O for the power. We will talk about that a little bit later. So, what have we got? This guy here tells us, this sign tells us whether A is consumed or produced. K is a constant. And the important thing is K can only be, without any exception, no, there is one exception, but K can only be positive. The only exception where you find a negative K is in the converter of the warp drive on the HSS Enterprise in Star Trek. Did you write that down? Yeah. Brilliant. That's the only case where K can be negative. Otherwise, K is positive. Can K be 0? What do you think? What would happen if the rate constant was 0? What would happen to the rate? Loud? Who said that? What would happen if K was 0? The rate would be 0. Absolutely right. Look at the equation. The rate would be 0. Nothing would happen. It would be dead boring. Yeah? So why bother? So usually K won't be 0 because something should happen. And we're only interested in what happens. So K can only be positive. If you ever do wild calculations and you come up with a negative K, Take a deep breath. Think of Captain Kirk. I hope some of you at least know Captain Kirk, yes? And go back to your equation. Oh, by the way, do you know how many ears does Captain Kirk have? You know?
Yeah.
How many? 3. Yes, you're absolutely right. Captain Kirk has 3 ears. A right ear, a left ear, and a final front ear. Ow. Sorry. It's a really bad one. Okay. K can only be positive, right? Now, A obviously is our, and K is a constant. It should not change during the course of the reaction. Now, Sod's law there are cases where K is not a constant. And where you think, bugger it. Why is it not a constant? Is that a really bizarre case, like I just said, you know, enterprise or something like that? Actually, not entirely sure how I should tell you that, but all the stuff that's happening in your body, unfortunately, follows these rate laws, but unfortunately, K in these reactions changes constantly. That's the only thing that's constant, that the constant is changing, which is, you know, sort of bloody hell, who came up with that? So if you have an enzyme reaction, K is changing all the time. Horrible stuff, enzymes, I tell you. You're going to hate them. Okay, A is just simply the concentration of our reactant. Now, what is this guy M here? M is described as the order of the reaction. It's the order of the reaction. And what is actually the meaning of this M? Well, M per se is just simply a part of a mathematical equation. This rate law here is just simply an equation. And M is nothing else but an exponent that makes this equation manageable and true. M does not have any other meaning. So M is just simply a mathematical expression that we use. Sometimes people come across another expression which is called molecularity. Molecularity is something totally different. Molecularity tells you how many compounds have to bump into each other in order for a reaction to happen. So how many atoms, molecules, whatever, need to interact in the slowest step of a reaction. So, this also goes into the next part. Molecularity can only be a whole number. You can only have, for example, 2 atoms bumping into each other. You can't have 2.5 atoms. What is 2.5 atoms? Well, 2.5 molecules. That doesn't make sense, yeah? Or 2.3 molecules or something like that. You can have 1 molecule. That is, for example, if the molecule just simply decomposes into something. So, for example, if you have radioactive decay, you have a radioisotope, and this radioisotope disintegrates into something. Then you have a molecularity of 1. You have 2 compounds coming together, then you have a molecularity of 2. What about 3? Can you have a molecularity of 3? 3 compounds coming together? Yeah? Yes, you can. In theory, it is possible, but it is extremely rare. And to my knowledge, there's only one reaction has been described as trimolecular, and that's a really, really weird thing, which you will never encounter. So, can the molecularity be 0? Basically meaning no molecule is reacting. Yeah, but that's a little bit like K being 0. Nothing happens. If I say no reaction is happening, I found something really interesting. No reaction is happening. Everybody goes like, yeah, right. What have you been smoking for breakfast?
Could it be 0 if there isn't a slower step?
There's always a slow step.
What if there's only 1 step?
If there's only 1 step, again, that's the slow step. Yeah? So, molecularity, you can only have 1 or 2. Okay? Now, order. I love that guy. I probably should, put that on a sort of a ringtone. Order. Sorry? I'm supposed to be not political here, right? Order, we said, is a mathematical concept and nothing else. It doesn't have any practical meaning. And as such, M, the rate order of a reaction, can be any number. M can be any number. It can be a whole number. 1, 2, 15, whatever. It can be a fractal. It can be 0.5, 1.253. It can be 0. Can it be negative? Yeah, you're absolutely right. It can be negative. It can be a negative number. Can it be an irrational number, like that never ends, like pi? Yeah, absolutely. The order can be anything, right? And the great thing is, in a reaction, the order will stay the same. It doesn't change. Actually, scratch that. That's not true. If you've got an enzyme reaction, as we will discover next term, we will find that the rate constant and the order are constantly changing, which is a pain in the backside, because you are constantly rewriting your rate equation, because it constantly changes, the bugger. But usually, for the purposes that we are dealing with in these simple kinetics, we assume it's constant, right? Last year, I had a really, really interesting discussion with a student who asked whether the rate order can be an imaginary number. So, for example, have you done imaginary numbers? No? It's basically an imaginary number would be the square root of -1. If you try to do that, you can't do it on your calculator, right? Because you can't do a square root of a negative number. But that is where imaginary numbers come from. They have sort of two components. They have a real and an imaginary aspect. And that guy asked, can the rate order be an imaginary number? And I thought, bloody hell, how do I know? So we did a little bit of digging around on the interweb, and Google is your friend. It looks like that nobody has thought about that. So I would argue, yes, it can be an imaginary number, but what on earth does it mean? And we have not yet decided on what this could be. However, if some of you find something about a rate order being an imaginary number, I would be incredibly interested in you telling me, because it has been bugging me for at least a year, and I couldn't find an answer to that, right? So if you find what a rate order being imaginary actually could mean in practical terms, you will get a little prize. Let me know. So these are the things. So we now can write a rate order, a rate equation, dA, if we have a reaction, A is converted into something, dA over dt equals minus k times a to the power of m. Fantastic. Now, of course, we want to figure out what is k, what is m. And we can do experiments for that. So how can we do that? Well, actually, here is a sort of a nice trick. In order to figure out k and m, what we can do is we can write, instead of dA and dt, we just simply write speed of the reaction. So speed equals plus or minus? Plus. It doesn't matter in this case because speed is always positive, right? So speed is positive. And we assume, even if it says velocity of the reaction, we just simply ignore, in this case, the sign. So you will sometimes find speed of the reaction or velocity of the reaction or even rate of the reaction. And why we, in this case, sort of drop the sign, I will show you in a minute. So speed equals k times a to the power of m. How do I find m in this case? How can I find m? You have the tools for that. You can figure it out, you know? Look at the graph. Well, we don't have a graph at the moment. How can I figure out m? I use the rules of logarithm. So, what have I got? I have log, and I just simply say rate, the absolute of the rate, that ignores the sign, equals, so we've got log k, the times sign converts into a plus sign, plus m times log a. Does that make sense? The m, the exponent, now becomes a factor. That's the rules of logarithm. Now I can write that in a slightly different form. I can write this as log rate equals m log a plus log k. That looks beautiful. That has a kind of aesthetic to it. Why? Hey, look at that. Y equals mx plus c. What's that? That's the equation. You're absolutely right. That's the equation for a straight line. How cool is that? So, what do we need to do? All we need to do is, from experimental data, we collect rates for different concentrations of A. And what we do is we plot our data on the y-axis. We just simply put log rate. And on the x-axis, we simply plot log concentration of A. Yeah? And I should get a straight line. I get a straight line like that. Can the straight line actually go into the negative range? What do you reckon? Can I have a negative log rate? Can I have a negative log rate? Yes or yes? Of course I can have a negative log rate. I can't have a negative rate in this case because a log of a negative number is not defined. But log rate can be negative. Well, just simply say log of 0.01. That would give you a negative number. Well, it's perfectly acceptable. So if you find something like that, that's absolutely fine. It's not a problem. A lot of people start hyperventilating when they see something like that. No, it's, you don't need to see the doc. It's absolutely fine. Can happen. Yeah, not a problem. And of course, we have the intercept here. And this, in this case, would be log k. It's not k, it's log k. Can log k be a negative number? Yeah, of course it can. If k is smaller than 1, for example, then log k would be a negative number. K cannot be itself a negative number. It's the log k that can be negative. Yeah? And of course, the gradient here, and I illustrate it like that, this m here is simply our rate order. So all I need to do is I need to figure out different substrate concentrations. So I have different substrate concentrations, let's say, A, 1, 2 in millimolar, 1, 2, 3, 4, and my rate. The unit for that would be, let's say, millimolar per second or so. 1, 4, 9, 16, let's say. If I want to figure out what is the rate, what is my order of the reaction, all I need to do is log A and log rate. Plot that, and from the gradient I see, what would it be here actually? What would be my m in this case be? You say second. And you say that with a little bit of hesitation, right? You say that with a little bit of hesitation. Now, I do the Chris Tarrant now with you, yeah, on Who Wants to Be a Millionaire. Second. Are you sure?
No.
No. Are you absolutely sure?
No.
How sure are you? You're absolutely right. Yeah? It is a second order. How do you know? Well, if I double my concentration, K times A to the power of 2. What happens if I, instead of 1A, have 2 A's? I then get 2A to the power of 2, but nothing else changes, so I've got 4 times the rate that I had previously. So I can immediately see this is a second order reaction. Yeah? Of course, you run into a slight problem with that if the order of the reaction is not a whole number, if it is a fractional number, if it is, say, 1.3 or something like that. You can't easily do that in your head. So you could use a graph, or you just simply use some techniques with solving 2 equations with a different technique. Now, there are practice questions on my wonderful website. I encourage you to look at that, because tomorrow we are going to look at some special cases. And there are some really interesting differences, for example, between men and women. And I'll show you these differences tomorrow. But don't get too excited. We don't do, Have a lovely day and enjoy your test.